All right, let's get started, please. Okay, your assignment number 4, please watch out for the deadline. Make sure you submit in time to claim your credits. Your makeup lecture has been posted. Let me just refer you to them very quickly. So you can look at basically right here, right? Makeup lecture for programming test number 2. Right? It's basically something about binary search deletion and also about how you can construct a heap, which I'll briefly mention today, and also how you can use an array rather than link structure to implement binary tree. So these are the topics that's covered in the makeup lecture. So you still have time to catch up with it before the exam. Okay. And the course evaluation, optional, but you still have a chance, until tonight. If you're interested, please do consider. And also, of course, office hour no more, right? But I'll try to hold some special office hour maybe next week a little bit. But I do have another course. They have their exam on Thursday, so I might need to give a little bit more time to them. But maybe after next Thursday, I can give more hours to you guys. I will also reach out maybe about some review session and also some example question as well. I'll give you guys some practice. But towards the end of today, after we cover everything, I'll wrap up the course very quickly, and then we can talk a little bit about the exam. I can give you guys some preliminary information. But before the exam, when I hold a review session, I can give you a little bit more concrete tips about what you can do. All right? So that will be the plan. Any question about the course in general? All right, so last class, let's just do the routine. Let's now do the recap, and then we'll move on to the last bit of the material. So last time, we actually spoke about searching for a binary search tree. So the critical points for you guys to remember, there are two cases. Either the search is successful, where you're going to return the internal nodes with the matching key. Or if the search is unsuccessful, in which case you're going to return the external nodes where the key can be safely stored over there. So the critical insight for you to remember or to review for the exam is this external node return has the predecessor and successor for the corresponding in order sequence over there. Right? You got to remember that's really to do with the sorting property about the binary search tree. So make sure you really understand where this external node should really be situated in the in order sorted sequence. That's the main thing for you guys to remember. And we talk about basically in the BST node how you can trace it in Java code. You can also take a look. Similar idea, just in the Java context. And we talk about the running time. So there are 3 ways to really consider the running time for searching. The most accurate way for saying that is it's going to be big O of h, where h is the height of the tree. And of course, there's no guarantee about how balanced the binary search tree is. So in the worst case, it could be linear time. So when you do a search on the binary search tree, in the worst case, it's no better than a linear search on an array. And the best case would be just log in which case you got the height being just log in. So that'll be the best case you will be hoping for. And the heap data structure we're going to introduce today, in some way, you can guarantee the heights to be exactly log in. It's not really exactly binary search tree, but I'm more talking about just the heights. It's going to be the minimum possible. All right, and then we talk about these 2 binary search tree, binary search number 1, binary search tree number 2. So in this case, the height is simply log n. And in this case, the height is actually n. Right? When you try to do the search on these 2 binary search tree, it's going to correspond to either a binary search on the sorted array, or it could be just a linear search on the array. Right? We had a detailed discussion on Tuesday. You can refer to it if necessary. Okay. And then we talk about insertion. Insertion is just a very slight extension to searching. So you definitely still have to search for the key or the entry you're trying to insert into the tree, right? So there are 2 cases. Again, it might either be is already existing or does not exist, right? So that's something you're gonna watch out for. And the running time for insertion is going to be dominated by the searching step, which will be log in. Okay. And we talk about if you start with some empty binary search tree and then try to insert certain series of keys and how the resulting binary search tree can look like. And this case over here, the height is simply linear, in which case if you try to do a search on that, it's no better than linear search really on a sorted array. So in this course, we don't really talk about how you can restore the balance whenever you actually got some ill-balanced binary search tree, but maybe in 3101, the subsequent course, you will learn more about it. But in some way, the heap data structure that we're going to talk about today, it has some flavor about fixing the property, which we'll see today. Okay. And then we talk about this high balance property for checking if a binary tree is actually balanced. And we talk about one case where it is balanced, and we talk about another case it is not balanced. You guys can also try to do the exercise over here, right? That's kind of important. And of course, to really solve this kind of exercise, you got to annotate the notes for their height bottom up, right? That's what we saw last time. You can refer to the lecture recording if necessary. So this was the last page that we spoke about, priority queue. So let's now review some basic facts about this priority queue, and we're going to dive into it a little bit deeper today. We're going to consider basically 3 possible implementations for priority queue. 2 of them are to do with the linked list, which are quite easy for us to consider. It will be a nice, review on the linked list, so that'll be also useful for your exam. And the 3rd implementation is going to be about using a heap, which is the most important, most efficient implementation. Okay. So for priority queue, it's a collection of entries. And the entry has a key value. The lower the key value, the higher the priority. So the lowest key value should be the highest priority. Whenever you want to remove something from the heap, whenever you want to remove something from the priority queue, you don't remove any arbitrary entry. You only remove the entry with the lowest key value or the highest priority. And also, multiple entries might share the same priority value, which is okay. So you can remove any one of them, because they're considered equally important or equally urgent. And you should really also try to compare the priority queue and first in, first out queue. Right? That's also a very important comparison. All right, any question from last time? Yeah.
So, for example, when it has like equal priority,
yeah.
then how does it sort that thing?
So we don't really sort entries with the equal priority, as you will see, let's say in the case of the heap. Heap is a very efficient way of implementing a priority queue. As you will see, somehow as long as certain property is satisfied among the keys, it doesn't really matter how you order them. As long as the minimum or the lowest value is retrieved, then I'll be okay. So for example, let's say, let's say this one is a minimum, is a unique minimum. We remove this one, let's say. And now what will be the next removal? As this will be 2 over here, right? Also unique minimum. And now, as far as the minimum concerned, we got either this or this. If I remove this one, that's okay, it's a minimum. But if I remove this one first, it's also fine, it's also a minimum. When the minimum is not really unique, you can remove either one.
So, like the minimum is not considered by the value it holds, but the priority.
Yeah, minimum is more like a priority. So as long as you can get the most urgent task to be retrieved, you're okay. Good. All right, let's now move on. So if you look at the slides, you will see slide number 6 summarizes about the basic operation for priority queue. You guys can take a look. And especially if you look at, for example, remove min. Remove min here, you can see the min, it's just about minimum key value or highest priority, really. Okay? You can look at the corresponding precondition and postcondition for each operation. But today, when we try to study the different implementation, we have to consider how to implement each one of these. Okay, we'll talk about them. Okay, priority queue. All right, so let's now talk about how we can implement priority queue. Let's say we start with something very basic. Let's say we're trying to use singly linked list, let's say. Okay, and we're going to consider 2 possible ways to use a singly linked list to implement priority queue. So we're going to fill out some table right here. Okay, I'm going to show you the table here. Okay, so this column here summarizes all the operation that's going to be needed for the priority queue ADT. Okay, so we're going to talk about size, whether or not it's empty, minimum, insert, and remove. And then we got 2 possible implementation. Either we have a sorted linked list, or we have an unsorted linked list. Either way, you can think about approach number 1 and approach number 2. And for each one of them, we ought to know how efficient it is to use that data structure to implement the priority queue operation. Just to give you a little bit more visual idea, approach number 1, if you got a singly linked list that's sorted, that means over here the head is going to be the minimum key value, always, right? So think about right here, it is the minimum key value. The minimum key value. Also, it's sorted, so we are saying that if you consider any adjacent nodes in the sorted list, their key value, ki and kj, it should be in the sorted order as well. The equal there is okay because we do allow duplicate of the priority for the key values, right? So that's about sorted. And for the unsorted, really not much to say. It's just unsorted. Doesn't matter how you order. So can the minimum be here? Not necessarily. Can the minimum be here? Maybe. Or minimum can be here as well. Can be anywhere in the list. So these are the two strategies we want to maintain to implement for priority queue. Let's now go over each one of the priority queue operation to see how efficiently it can be implemented using sorted list versus unsorted list. Okay. Let's start with something very simple, which I wouldn't bother you. What about the size and empty? Should be efficient, right? Remember we talked about trading space for time, right? Remember that principle we said earlier. So we can say trading the space for time. We can simply declare some attribute for storing the size of the priority queue or the list. In that case, getting the size or checking to see whether the size is empty, right? Should be constant time operation for both. Very efficient. And let's now consider the minimum operation. So let's say I want to retrieve from the priority queue the entry with the lowest key value. Okay. Now, in approach number one, how efficient is that? Constant or linear or something else? Well, sorted, right? Should be constant. Right here, all right? Unsorted, no guarantee. We got to write a loop to go over one by one until we find the minimum. You got to do a linear scan, right? All right, so it's going to be big O of 1, and symmetrically, that one there is going to be big O of n, because you got to search for the minimum. Interestingly, what is efficient for this one here is inefficient for the other one. All right. Now, what about insert? Let's say we want to expand the priority queue. If I want to insert the priority queue by one more entry, in the case of the unsorted list, since this list is already unsorted, it doesn't matter where I insert it into. It just becomes still unsorted. So maybe I can just insert it first. In that case, I can set the references, which will be constant time, right? So that one there will be big O of 1. On the other hand, what about insert into sorted list? That's not that trivial, right? Remember insertion sort. We keep the part of the list to be sorted. Now, how can we expand that sorted area? We're going to insert into the right spot, right? So you got to run a loop. So that will be linear time. Right? So you can think about, let's see, if I want to insert into this sorted list, it may be here, or maybe all the way here. So in the worst case, you had to scan through the whole list and insert it into the right spot. So that will be big O of n. Again, what is expensive over here is actually cheap in the other one. Final one. What about I want to just remove the minimum? Well, this one is very similar to minimum, actually. In the sorted list, I know that the minimum is just ahead. I can remove first, which is constant time. And in the case of the unsorted list, I need to find out where the minimum is, first of all. To find it, it's big O of n. So to remove it, just add some constant time. So that will still be linear. Okay. So big O of 1 and big O of n. So this kind of table is something you really want to draw by yourself. Later on, when you're trying to design your own algorithm or data structure, you want to consider different alternative implementation strategy and see what the corresponding running time is. That's a very important technique to actually apply when you're designing your own data structure. All right, just a final concluding remark. So what's the conclusion over here? Now that we get a running time for strategy number 1 and strategy number 2, the follow-up question is, under what circumstances should I choose strategy number 1 as opposed to 2, right? So something you can say over here, which is very straightforward. Approach number 1, if the usage demands more about minimum and remove min, which are cheap, I should really choose strategy number 1. If they got more infrequent demand for expanding the queue, I can also choose it. Right? You can also symmetrically for the other one. Okay, I'll write it down for you. So this one will be the more suitable strategy if, for example, condition 1, we got frequent, minimum, and remove min. Frequent retrieval and also removal of the top priority entries. Minimum entries, basically, minimum key. And condition number 2, let's say for insert, if that's really not very frequent, that means it's infrequent. In that way, I can also choose it because I don't need to call the expensive operation for many times. Infrequent. Expansion to the priority queue. Right? And as for the more suitable condition for unsorted list, it's exactly the opposite. Right? That one you can do as exercise. Question?
Yeah, I'm a little bit confused with the insert and the unsorted list because the way like I'm imagining it, I feel it like in my mind it's like both of them should be the same and inserting them into the right spot.
No, in the unsorted case, because the list is unsorted, so it doesn't matter which where you actually insert it. It will still be unsorted, right?
It wouldn't matter.
Yeah, it wouldn't matter. If you insert in the middle somewhere or insert it at the end, it's still unsorted. There's no way for you to sort that list anyway, right? That's why, yeah. All right, any other questions about this? All right, so we talk about 2 kind of naive implementation strategies for priority queue, but the ultimate strategy you should really use for implementing priority queue should be a heap, which we're going to talk about. Okay, we'll get there. All right, let's now talk about the final data structure for this course, which is a heap. And by the way, for those of you who might be confused with another term, also called heap, if you took a 2031 in the previous term, they also talk about heap as opposed to stack, right? Heap is more like a more permanent memory space where you're going to store maybe some data there. It has nothing to do with the heap over here. They just use the same word. Nothing to do with this, right? Don't get confused. The heap we're talking about here is a specialized kind of tree. Okay, just to clarify. All right, if you look at the slides, we are now done with slide number 7, which is the table. And then let's now talk about heap. Okay, let's go over some definition quickly. Okay, a heap is basically a binary tree which will satisfy certain properties. So there are 2 properties we're going to go over today. One of them you already studied in the previous lecture where we talk about binary tree. So for that one there, I can just remind you about the basic facts. But the other one is something new that we need to spend a little bit more time. All right, the heap stores entry. Each entry has a key and value, but we're going to focus more on the key value. Okay, the lower the key, the higher the priority. And this is just one example over here, right? We're going to go over that in a moment. So there are 2 properties we're going to satisfy in order for a binary tree to be a heap. One of them is called a relational property. It's to do with the relation between child and parents, which we'll see. And the second property is called structural property. It's to do with how the tree nodes are organized at different levels. Okay, so these are the 2 properties. All right, let's now talk about one by one. Okay, let me talk about structural first. Okay, and then relational. Doesn't really matter, but just a little bit more sensical order. The structure over here tells you that in order to be a heap, the binary tree must be a complete binary tree. And we learned about this, right, earlier, about what it means for a binary tree to be a complete binary tree. You can look at the slides. So these are the 3 conditions that we studied earlier. So I may not repeat them right now. You can definitely review from the previous lecture material. Okay, but I can visualize them to you very quickly. Okay, let's talk about the first one. So that's what I call the structural property. Okay, and then structural, and then it should be a complete binary tree. Right? There are 3 conditions over there, so you got to review them. And the structural property is actually very important because it guarantees about the heights of the tree. So that one there guarantees about the heights of the tree, which is log n. So in some way, the heap is a balanced binary search tree. Oh, I beg your pardon, take it back. The heap is a balanced binary tree, nothing to do with search property, right? Don't get confused. So the heap is a balanced binary tree. How do we know? So let's look at the different levels over here. Let's just remind you quickly. So we got this level over here, and we got this level over here, and also we got this level over here, right? So if you recall, we actually got level H minus 1, level H minus 2, right? You can look at the definitions for a complete binary tree and try to look at each one of them. And to be a complete binary tree, the height would just be log n, guaranteed. And that's also something we said earlier. So the H is just going to be log n. Take the floor. And some basic facts about what a complete binary tree is. So we talk about here from level 0 all the way down to level H minus 1. Everything except for the last level. And we talk about how many nodes are there. Okay? That will be something you have to review. So here we say the number of nodes from levels 0 to H minus 1. Okay, I'll remind you, 2 to the H minus 1. Okay, to see exactly how to derive this number here, you can refer to the lecture materials earlier. Okay, just about that part. And for level H, there's a range for the final level here. Does not need to be completely filled out, as long as it's from left to right. Okay, and so that's why we got a minimum number of nodes and also maximum number of nodes. So the minimum number of nodes versus the maximum number of nodes. Both of them will consist of this common part over here, which is 2 to the H minus 1, and also 2 to the H minus 1. In the minimum case, we're saying that there's only one node at the bottom level, only one, right? That's a minimum. And the maximum will be when this level here is completely the maximum, which is 2 to the H, right? So this part here is going to be plus 1 and plus 2 to the H. All right, that's something we went over earlier. And if you want to simplify it, we can do that. So this part here is simply 2 to the H. And this part here is 2 to the H plus 1 minus 1. Okay. Some basic facts from before. So think about the structural property here is a necessary condition to be a heap, but it's not sufficient condition. To be sufficient, you got to satisfy both. Well, we're going to talk about the other one in just 1 second. Okay. All right, any question about the structural property? Not much to say. That's something we learned earlier. Right? All right, let's now go to the new property you guys gotta learn, okay? It is something called the relational property, which will be on slide number 9, okay? And you can say that as a relational property, but the more formal term is called heap order property, right? It's really for the heap, okay? And the heap property here is as simple as this. You gotta consider every node other than the root in the tree. And the key of the node must be larger than or equal to the key of its parent. That's the definition for heap order property. Okay? Let's now visualize that on some example to see exactly how to understand it. Okay? For example, if you look at this tree over here, it's actually a heap. For example, you can see that this node here, 5, larger than or equal to 4. 9, larger than or equal to 5, and etc. Right? If you try to do that kind of check, you will see that it's satisfied for every node. Let's talk about different properties from the relational property. Okay. Number 1. Any leaf to root path has a sorted sequence of key values. And to be more precise, it's the non-ascending order, meaning that's kind of decreasing, will stay flat because we allow duplicates. Non-ascending order. Okay, let's see some example here. Okay, I'll show you two examples. For example, let's say leaf to root. Path number 1. Let's say we got this one here. Oh, sorry. This one. Okay, do better. This one here. This one here. Okay, path number 1. If you look at key value, 12, 9, 5, and 4, decreasing. All right, another one, 13, 7, 6, and 4, also decreasing. Right? If you do that for every leaf to root or ancestor path in the tree, you're going to get non-ascending order for the key. That's property number 1. And property number 2 somehow can be derived from property number 1. Okay? So property number 2. Where is the minimum key according to property number 1? The root, exactly, right? This is the most important insight you want to remember. So somehow the values in the heap is not much constraint as long as the root has the minimum key value with respect to all the nodes in that particular subtree. Okay, I'll make it clear to you. Okay, so property number 2, the minimum key exists in the root. Okay, I'll give you two examples here. So let's say as far as the whole tree is concerned, it's a subtree, the biggest subtree we have. If you look at the root over here, this is the minimum key of the whole tree. On the other hand, if you consider this subtree over here, for that particular subtree, the root has the key 5. That tells you this 5 here is the minimum among all the key values in this particular subtree. Okay, that also makes sense. It's a recursive concept. So that's the minimum key of this subtree. All right, the final property. Okay, the final property also tells you that we only exist between the child and the parent about their key values. Between siblings, we don't have any constraint. It doesn't really matter if the sibling actually has any order among the keys. Okay, I'm going to write it down. So property number 3, the key between the left subtree and also right subtree are not related in any way or are not constrained in any way. Which means you don't need to worry about them when you check to see whether the binary tree is actually a heap. For example, if you look at 15 here and the 9 here, somehow they just happen to be, right? They are not related. All you care about these two keys over here is 15 larger than or equal to 5, and also 9 larger than or equal to 5. That's all you care. You don't care how these two keys are related, right? They are not the child parents. All right, so these are the 3 most important properties about the relational, right? But just remember, everything are derived from this particular one here. Whenever you talk about any node other than the root, the key of that should be larger than or equal to the parents. Okay? All right, any question? All right, good. Why don't we do a little bit like a warm-up exercises just to see how a heap can look like in some more concrete example, and then we'll do some more complicated operation. Okay. Okay, let's now try this one here. Right here. Okay. I got 1, 2, 3, 4, 5, 6 6 different trees over here. Let's now decide one by one whether or not they are heaps. Of course, in order to be a heap, you must satisfy both the complete binary tree property and also the heap order property, both of them, right? What about the first one? Is this a heap? It is. It's kind of the simplest one. To put it in another way, you cannot really find any violation about the full binary tree property and also heap order property. It simply has no children, right? So that is the smallest possible one-node heap. So it's kind of interesting. When you look at this one here, you can say it's a binary search tree. You can also say it's a complete binary tree. You can also say it's a heap because it's just the base case, right? So smallest possible one-node heap. Okay, just handle the simplest case. All right. Is this a heap? All right. First of all, it satisfies the structural property because at the bottom level, you go from left to right, just the left. And also 6 larger than or equal to 4. Good. All right. There's a left reference. This one? It is a complete binary tree, but it does not satisfy heap order property. All right. So this one here is complete, but violates heap order property because 4 larger than or equal to 6 is actually false. How about this one here? All right, why? Not complete. Exactly, because in order to be complete, you got to make sure you fill out from left to right. All right, you satisfy the heap order property, but not the structural property. All right, so this one here is not complete, but satisfy the heap order property. All right. How about these two? They are, okay? The reason I want to mention this is these are full binary tree. And if you remember, full binary tree means they are also complete binary tree automatically, like a maximum case, right? I just want to remind you about this logical relation. Being a full binary tree implies it's also a complete binary tree. So both of these are good. Okay. 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 Let me just make sure the recording went through. All right. So there are 2 heap operations I want to illustrate to you together. One is about insertion. The other one is about deletion. Right. So let's just get prepared to draw. Both of them are quite sophisticated to actually go through. Okay. So let me show you how you should really study this. If you look at the slides, you will see that on slide number, so now we are done with 9 and 10 about the 2 properties. So and this one we also done, right, about a different example for the heap or not heap. Okay, heap operation. So the one we are not really going to mention in the lecture is how do you extract the minimum key? Just return the root. That one's simple, right? It's a constant time operation. Just return the reference of the root. The other 2 we're going to talk about is about insertion and also deletion. And I'm telling you the running time right away, right? Both of them will just be log n, guaranteed, because it's a complete binary tree. Now we're going to see exactly how log n is going to happen. Okay, we'll see. And these 2 are really the foundation for performing a heap sort, which I will mention as the last thing today. Okay. All right, so let's now, and also it's very important when after either a single insertion or a single deletion, you want to make sure the heap remains to be still a heap, meaning that relational and structural properties must be maintained. And we'll talk about one by one. Slide number 13 is about the insertion, and in the slide you can see some like a pseudocode kind of itemized version of the algorithm. You can go over them when you study, but I'm going to illustrate to you exactly how it can be operated visually. Okay, let's now take a look. Okay. Insertion. Let's say we're given a heap over here. You can double check yourself. What we start with is a heap. Okay, you can check the structural and also relational properties. Let's say we now want to add a new entry right here with the key 2 and also data value t. But we're going to focus more on the t value here. That's what's important. Okay. How do we insert, right? Let's now try to see how we can satisfy the structural property first after the insertion, right? In this case, apparently there are two choices for us. Either we can insert as a left child, or we can insert it as a right child. Which one? Or both, or either? In order to maintain the structural property. Left child, right? Because if you insert it as a right child, it's not complete anymore. You're digging yourself a hole for fixing more. All right? So step number one, you want to really insert a new entry as a new rightmost node at this particular level, right? So that's really something you gotta remember as a first step. So visually speaking, you can think about this part here is level H. Okay? And then I want to insert a rightmost node right here, which will be the left child. Sometimes it could be the right child. Let's say if I already got something here, of course I got to insert as a right child. But if you already got the tree completely full, what should I do? Expand the level to be another one. Right? So these are like boundary cases you got to look after for when you write a code. But for now, let's say we're going to insert this as a left child. So step number one is going to be, we're going to create a left child right here. And that one there is going to store the new entry. Let me draw better. Okay. So that one there is going to be 2 and t. That one there. Right? So step number one. Store the new entry as the rightmost node at the bottom level, level H. Okay, the rightmost over here is important to make sure you still maintain the resulting tree to be a complete binary tree. But relational property, we're going to deal with that subsequently. All right, so now, is this a heap? Not really, right? Because, for example, if you look at that, 2 larger than or equal to 20 is not the case. All right, so we're going to do something about it. Okay. So what we're going to do is something called up-heap bobbling process. Okay. So think about we got the heights of the tree right here, log n, guaranteed. And it's something called up-heap bobbling. In the sense that we have to keep doing this step as long as we find there's any violation of the heap order property. As soon as we don't find any further violation, we can stop. We don't necessarily have to go all the way to the root, but in the worst case, we still got to go there. But even in the worst case, the tree height is bound to be log n. So log n is the worst case running time. All right, that's something I want to mention before I start doing it. All right, let's now take a look. Step number 2. I'm going to, for each step from now on, I'm going to identify 2 references, C for child and P for parents. So start with this. So this is the child, and this is the parents. For each node, it has a unique parents, always. So it's really easy to identify the child and the parents, C and P. And for step number 2, I'm going to check to see whether or not they satisfy the heap order property. The key of the child larger than or equal to the key of the parents. The key of the child is 2. The key of the parents is 20. 2 larger than or equal to 20, false. So I have some violation. Okay? If I have some violation, I should do something called a swap. I should really swap these 2 nodes. All right, so how do I swap? Well, visually it's easy. Move this and move this, right? So 2t should be here, and 20b should be here. So now, as far as this parent child is concerned, 20 larger than or equal to 2, I'm good. But in the global context, I'm still violating. For example, you can see 2 larger than or equal to 6, I'm still violating it. So we've got to keep going. We don't really need to justify this step, but as long as you follow through the ancestor's path from the leaf all the way to the root, in the worst case, you're fine. You don't need to worry about any other path. Okay? For that one, we don't need to justify for correctness. All right, so for step number 2, we have done this check. Okay? Let's now do step number 3. So for step number 3, this is not P anymore, so this itself will be a child. And we want to get its parents. Right, C and P. And then let's now do some similar check for relational property. So the key of the child larger than or equal to the key of the parents. The key of the child is 20 versus 6. 20 larger than or equal to 6. Oh, did I do something? Oh, beg your pardon. I did something wrong. Okay. Let me undo. Yes, exactly. Got to be careful, right? That's exactly the kind of mistake you might make in the exam. Don't be like me. Okay? I really meant to compare 2 over here and 6 over here, right? Because after the swap. Okay? So 2 here and also the 6 over here. All right? So 2 larger than or equal to 6 is false. Okay? That means I got to do another swap. And if I do another swap, I'm going to swap these two. So that means 6z will be here, and 2t will be here, right? So that is step number 3. But it seems like we're still violating the relational property, right? If you look at that, 2 and 4, not good, right? So what we do is we're going to do another one. So let's say here we're going to say this is not P anymore. This is going to be the child. And this is going to be the parents. And for step number 4, we're going to check to see whether the key of the child larger than or equal to key of the parents. Key of the child is going to be 2 and 4. So 2 larger than or equal to 4, false. Right? We got another violation. So another swap. Another swap. Swap these two. So 2t and also 4c. So now we reach the root. Now it's time to really stop. Right? You can implement this process here either recursively or iteratively. It's completely up to you. Right? And then let's see the final outcome. We got 2t, 4c, 6z, and also 20b. And we basically do the upheave bobbling to really propagate, to really promote this all the way to the top, because 2 happens to be the minimum of the key. That's exactly what we're doing. Okay. Any question about the steps over here? We're good? Okay, let's talk about running time. First of all, let's think about how many levels we need to really do the upheave bobbling. It really corresponds to the height of the tree. So the number of levels should be big O of log n. And this log n here really comes from the fact that we got a complete binary tree. Number of levels. And for each level, what do we do? For example, if you look at step number 2 over here, we got to do some comparison, and we might need to do a swap. So 2 things. Each one of them is simply a constant time operation. This one apparently just compares a relational operator, and when you do the swap, it's just about changing references about the parent and child. That's also constant time. And each level will be, number 1, compare. Number 2, about the swap. Both of them, big O of 1. You got log n levels. For each level is constant time. So overall, it's going to be big O of 1 times log n. Of course, it's just big O of log n. So that is the running time for insertion. Okay. So inserting into a heap is a log n time operation, which is not bad. Any question? You can see in some way the design for this data structure is very clever, right? You got a separation of concern about complete property there and also relational property. All you care is the minimum should be in the root. as we'll see later in the heap sort, you're going to use that minimum key in the root property so badly. We'll see. Okay? And let's now do deletion. Deletion in some way is very symmetric to insertion. So for insertion, we somehow have to do up heap bobbling, but for removal, we're going to do down heap bobbling. And there will be slight extra complication we have to do at every step, but it's not too bad, right? Okay, let's take a look. The same heap, and then let's now do some deletion. So the deletion here is going to actually, whenever we talk about deletion from the heap, we don't delete any arbitrary element or arbitrary node from the heap. You delete the root, basically. You're going to delete the entry with the minimum key, which is the root. But you don't just delete the root directly, in which case you don't know how to deal with these two subtrees. All right? So we want to do it in a way that's going to satisfy the structural property right away. Before, we said that to really add a new node, we got to add it as, we got to add a new node, we got to add it as a rightmost at the same level, level H. But now if we want to delete a node, we're just going to delete the rightmost node here. Delete this one here and use it to replace the root. That's the step to make sure we got the structural property maintained. From there, we'll try to fix the relational property. Okay? Just the way it is. Okay? Let's now document the step and we'll do it. So step number 1. Okay, we're going to store into some variable k from, so let's say this is the root, the key of the root. So this is the minimum value we're going to return eventually, right? So I can tell you that it's going to be step number 1, 2, 3, 4. Okay, step number 5. Okay, it's going to be step number 5 eventually. We're going to return k. Now we still got the intermediate step to really finish, right? And as part of step number 1, we're going to replace the root. Replace the root by the rightmost node at level H. Right? Get rid of this. Use it to replace 13W. In some way, the root is gone, and the rightmost node just get promoted unconditionally to the root. Is this a heap? Partially because it satisfies the structural property, right? Still complete, but relational not necessarily. For example, you can see that 5 larger than or equal to 13, wrong. So we got some work to do. So the process is going to be downwards because now this is where the violation will occur. So we should start from that rather than from the leaf, right? Here's the tricky thing. Before, when we try to fix upwards, because of the definition for a tree, you always got a unique parent. So you can always go like that without worrying about choosing which node as the parents. But now, here's a problem. If I try to fix from here, should I go to here or should I go to here? That's the issue here. But luckily, we have some very concrete steps to follow as part of the down heap bobbling. Okay, I'll tell you in just one moment. But first of all, let me just mention the name of the process over here. So this is the height of the tree, which we know is log n. It's something called down heap bobbling. Okay, down heap as opposed to up heap. And here is the principle. First of all, you identify this node here as a parent. But which one should be the child, left or right? You're going to compare the key values of the two child nodes and choose the smaller key. In this case, 5. So this is the child with smaller key. So this will be the C. And we do exactly what we did for heap bubbling. So step number 2, which is on the right here. We check to see whether the key for the child larger than or equal to the key of the parents. The key of the child is 5. The key of the parent is 4. So 5, key of the child. Oh, I make the same mistake again, as you can see. It should be 13 rather than 4, right? Okay. Hopefully only me, not you guys. All right. So now 5 larger than or equal to 13, false. So we should swap. Okay, so we swap these two. So 13W should be here, and also 5A should be here, the new root. But if you look at that, 13 larger than or equal to 5, and 6 larger than or equal to 5. Think about it in this way. If we chose the child with a larger key, that means we would have put 6Z over here, and think about the consequence. It's going to violate the relational property. Yeah?
What if both keys were 5?
It doesn't matter which one you choose.
Okay.
Yeah. Good question. Yeah. If both of them are, because somehow we don't really constrain about which, like how these two siblings are related, it can go either way. Okay. Yeah. Good question. All right, so the second step is done right here. Okay, so now let's identify the parents and the child. So this one is not child anymore, it's going to be the parents. And now, should we choose this one here or this one here? Left or right? Right, because this one is smaller. Okay, so this is the child with smaller key. Okay. And then we're going to do some comparison right here. And that one there is going to be the key of the child larger than or equal to the key of the parents. The key of the child will be just 9. And versus 13. 9 larger than or equal to 13, false. And we're going to do a swap. Again, this one and this one. So 9F should be here, and 13W should be here. We don't necessarily have to go all the way down to a leaf, but in the worst case, we may have to, which is okay. It's still bound to be a log n because of the complete nature. All right, let's now take a look. So, by the way, I should have put the C over here. Okay. Remember, that's a parent and that's a child with a smaller key value, right? That's something you want to keep, make sure you kind of keep track. What is the P, what is the C? All right, so the final one, this is not C anymore, and this one should be the P. Left or right? Right, because smaller, all right? The child with smaller key. Which is good. And then we're just going to get the C over here. And let's now do one more comparison. That'll be step number 4. So the key of the child larger than or equal to the key of the parents. Key of the child is actually 12 versus 13. So 12 larger than or equal to 13, false. So we should do one more swap. Swap these two. So this will be 13W, and this will be 12H. Brian?
Sorry, this might be a weird question. But
Yeah.
if they were the same, wouldn't you know exactly where to put it? Because it came from the bottom right, and they're both 5. If the two children are the same, so you'd know exactly where to put it. You wouldn't even have to iterate. Well, I'm sure you'd have to iterate down to it. But
How about we discuss this right after class, so I can properly process exactly what you meant. Yeah. All right, so let's now take a quick look. So we got these steps, step number 2, 3, and also 4, right? Also, step number 5 is to return the final key value after we have done the down heap bubbling. And then let's see the contents of the heap afterwards. We got 5A, we got 9F, we got 12H, and then we got 13W. All right, if you double check, the whole heap is now a heap. really, satisfying both the complete and also heap order property. Okay, running time. Similar as before, you want to think about how many levels. The number of levels is going to be basically big O of log n, because it's a complete binary tree. And also, each level here is slightly more complicated. Because, for example, you can see that over here. Let's say when we are here. Number one, we're going to identify the child with a smaller key, in this case. So you got to compare 6 and 5, right? That's one. And then you got to compare the relational property, and also got to do a swap. So 3 things. But each one of them is primitive operation, just comparison, and changing the references. But for completeness, let's write it here. One is about you got to choose the child by choosing the smaller key. And also you want to compare. And also you want to swap. But all these together will just be constant time. So you got log n level. Each level will be constant time. So you still got log n. So overall, you got big O of 1 times log n, which will be just big O of log n. So that is the running time for deletion, which is nice. So both insertion or deletion work when you try to shrink a heap or try to grow a heap, log n time. Way better than linear. These 2 operations will give you the foundation for heap sort. Okay? All right, any question? Okay, I would suggest we take a very short break. So before the break, we did the insertion and also deletion. You guys can take a look at the textual description here, and just to make sure you grasp all the information here, and some illustration, but that's pretty much what we did. And deletion as well. Both of them log n operation. And we have done so much hard work just because we want to now do heap sort. Okay, so this is a very important facts about the different operation on the heap. If you just want to extract the minimum, big O of 1, just return the root. If you want to insert or delete, log n. You can compare this, these two, this table here with the list-based implementation. And let's now, so there's another few slides about how you can construct a heap out of an array. So that will be part of your makeup lecture that I assign you to you to study, right? So you can take a look. It's already on the lecture site. So these two are also very practical techniques for you to grasp. I'll let you study them. So it's either top-down or bottom-up heap construction. Okay, you can take a look. And I'll mention about their running time in a moment. Right, heap sort. Okay, we actually mentioned about this heap sorting algorithm since day 1 of the course, right? But in order to really do a heap sort, you want to understand what a heap is. To really do that, you got to understand what a tree, binary tree, balanced tree, complete tree, so many things together, right? So now will be the time to synthesize everything together into a sorting algorithm. Okay, and let's see what a sorting problem is. It's really the same problem as selection sort, merge sort, quick sort, insertion sort. Just the same problem, but we're coding the solution differently. You got an array of numbers, and then you simply return just another array that's in sorting order, right? How do you do heap sort? Just before I tell you the idea, it's actually pretty simple. If you're thinking this way, if you're given an array, if I tell you that you can somehow construct a heap out of the array, so now you got a heap, storing everything. We know that the root will always give you the minimum. What if I keep removing the root from the tree until it's empty? That means I keep getting minimum from there. Wouldn't that be sorted? Isn't this something we did earlier? What is that? I keep selecting the minimum. I'm already telling you the answer. I keep selecting the minimum until I got selection sort. However, you may want to ask yourself this question. If somehow heap sort is so much like selection sort, why is heap sort will end up being n log n, but selection sort is actually n squared? Keep that in mind. Oh, Josh, you got the answer already. Go ahead. The highs, right? Okay, well, I'll talk about it as well. Because if you select from the array for minimum, it's always linear. But if you try to select the minimum from the tree, it's constant time. However, when you remove it, you got to do some downward bobbling, which will be log n. All right, that's something we can see a little bit later. All right, so let's now talk about heap sort, right? I'm going to sketch the idea with you and tell you exactly how that works. You can feel free to implement this yourself, okay? Quite a fun exercise to do. So when we talk about heap sort, what we'll see is eventually it's going to be big O of n log n. Oh, thank you. Thank you so much. Oops. There we go. Thank you. N log n. Okay. So that's the final outcome we're going to see. Let's say we're given the input array that is not sorted. And then we simply got n entries. Step number one, we're going to construct a heap, like a tree, out of the array. So step number one, we are actually going to construct a heap out of n entries. So there are two ways for you to do this. Either you do top down or bottom up. So that's the topic for your makeup lecture, right? So for now, I'm just putting them as a placeholder, okay? So you got to make sure you fill out the details before the exam. Either you can go for approach number one, top-down approach. Or you can go for approach number two, it's the bottom-up approach. The top-down version, as you will see later, that one there is also big O of n log n. And the bottom-up approach is slightly more efficient. It will be linear time. But the bottom-up is slightly more complicated to understand, but you will see. Okay? So you can either go for n log n or linear construction. But it doesn't really matter which you choose, because once we get to the second phase for the heap sort, it's going to be n log n anyway. So asymptotically, doesn't matter about the first phase, okay? As long as do it properly. All right, so now let's say after this, what you get is a heap satisfying the relational and structural property. And so this is a heap. And the root is always the minimum, guarantee. And the principle is we're going to exploit the heap order property. The heap order property or the relational property by continuing to delete and extract the minimum or the root key value until the tree is empty. So you might need just a loop to say, I keep removing the root from the heap until it's empty. And every time I retrieve the root, it's guaranteed to be the minimum. So I'm basically appending minimum after minimum after minimum. And just to remind you, this is very similar to how we did it for selection sort. However, for selection sort, each selection is about big O of n. On the other hand, for each minimum over here, if I actually want to extract the minimum, it's going to be big O of log n. Right? Remember, removal is going to be log n, right? So that's why it turns out selection sort is going to be n times n. And for this one here, it's n times log n. So, right? That's some meaningful comparison you want to do. All right, so finally, I want to mention about how you can understand the running time. You can also look at the slides for a little bit more detail. So by implementing this, right, so the runtime is going to be big O of n times log n. And the log n over here is really about the each deletion, which involves the downward bobbling. And the n here is about how many deletion do you need to go from n nodes down to no nodes until empty. So the ideas about heap sort is incredibly simple at a high level. Construct a heap and keep deleting the root until it's empty. However, to really understand why this works is not trivial. You have to understand what a heap is and what the running time is for insertion and deletion, and also about the construction mechanism. Okay. All right, question. All right. So that will be the last bit I want to talk about for the course. Okay. And the remaining part will be some makeup lecture for you to catch up. All right. So after this, we also got one more, which is about how you can implement a binary tree using an array as opposed to linked node. Right? Just another alternative for you to use. You can feel free to use it as a practical application. Okay, you can take a look in the makeup lecture, and then we are done with this lecture here. All right. Any questions about heap in general? Yeah.
Are we going to have the reference code for heap sort?
We don't actually. I don't have that, but feel free to implement it by yourself. Okay, exactly how you implement this is going to be some programming challenge for sure, but it's not too bad as long as you get the idea. Yeah. Alrighty. Okay, let me wrap up the course very quickly, just a few minutes, and then we can talk about the exam. Okay, we should have enough time. Okay, if you don't mind, let me just make sure. All right, so let's see what we have learned so far in the course. It's not really exhaustive list, but at least the major topics we have covered. Definitely programming, lots of JUnit testing in your assignments, and also recursion. Definitely we have done a lot, not just on linear array, but also on the trees as well. And also generics a lot, right? So I think I can take these techniques about Java programming. Maybe when you get to 3311 software design, it can also lead you a long way, right? So these are very practical techniques for you to keep. Data structures. We definitely talk about arrays and also circular array. Don't forget, it's part of your makeup lecture for the Q, right? Make a circular array. Make sure you study that. And singly linked list versus doubly linked list, right? We spent quite a bit of time before the reading week talking about it. Also stacks, queues, and also double-ended queue. Also very important, okay? And also we got trees, wow, all kinds of tree. We got trees, binary search tree, balanced binary search tree, also complete tree, full binary tree, proper binary tree, right? We got so many, right? Just make sure you review them. And priority queues and also heaps, which we spoke about today. Algorithm. As syntactic analysis, we kind of show you the basics about how you can prove things or to given some piece of code or even given some high-level sketch, how you can figure out the running time. So I think these are all important stuff. Binary search and also all kinds of sorting, right? We have done all of them, okay? Insertion sort, selection sort, merge sort, quick sort, and heap sort. These are all the standard ones, right? I think I'm glad actually we covered all of them. And also the different traversal mechanism, pre-order, in-order, post-order, right? All right, so beyond this course, I do have two suggestions, right? If you want to go a little bit further, maybe in the summer, if you want to do a little bit more self-study. This is like a standard textbook, by 3101. People really use it. So I think you don't really just want to make algorithm working on your paper. Algorithms are meant to be implemented and working on your system. So I would suggest take the book, either online, I mean a legitimate copy, of course, buy it online, or also get a physical copy. It's really worth having one on your bookshelf. You can really try to maybe understand mathematical analysis and try to implement it in Java or whatever language you like. It's a very good long-term investments for you. Okay, that's something I always suggest. Give it a try if you want to. And I also mentioned about compiler as part of the motivating, one of the motivation for this course. So now that you guys learn about trees and recursion, you have all the technical foundation to start implementing a compiler. You got everything you need. Okay, so this EECS2101X is about compiler. I taught it before, maybe 2 times. I'm going to teach it again in the summer. But there's a tutorial video there showing you how you can build a compiler from scratch. And it's in Java. For those of you who might be interested, check it out. You can build some small compiler from there, get some inspiration, and think about how you can build some bigger compiler yourself. Okay? And compiler is really a very nice way to synthesize about trees and recursion, and also software design technique. As you go to 3311, software design, your professor most likely will teach you something about design patterns for OO. Two of them are something called composite and visitor design patterns. So these are all to do with trees, right? So after 2101, implementing compiler is really a very natural way to move forward, okay? So I hope some of you can give it a try. All right, so in the third year, so what you learn in 2101 will be assumed for sure. And then we didn't really cover hash table, but for those of you who really want to grasp some basics, you can feel free to go to my previous teaching in 2030. Somehow I covered that a little bit about hash table. You can feel free to check it out. But it's not going to be covered in the exam, okay? For graphs, definitely we cover extensively in 3101. Some of you were asking if you want to take some more advanced course with me. In the fall, I will be teaching a course called 3342. This one is more about applying the 1090 logic kind of stuff into system developments. Like I see, it's more concrete application of 1090 logic. If you're interested, it's software engineering core courses. And also 3101. I'm going to teach that for the first time in fall 25 and winter 26. If you want to take it with me, you can also, maybe nice to see you, or you want to avoid me, maybe I wouldn't see you, right? Either way. Okay. All right, that's about the course. Thank you guys so much. Okay. Thank you. Thank you. Okay, exam. What a nice transition, huh? Okay, exam. I think today I can give you guys some preliminary information so you can get started preparing. But I'm going to host some maybe at least one review session. I can give you guys a little bit more concrete tips in the review session, okay? Because I don't really know exactly the question there just yet. But I can tell you roughly, okay? We got 4 minutes, but we can take as long as needed. I think that will be your best interest. Okay, let's start with the exam here. So for exam, so we'll give you 1 or 2 review sessions and also some office hour. I'll reach out to you. Just make sure you check your email all the time, right, during the exam period. And I will also give you guys like a PDF guide, like for the written test a little bit later. Okay, I'll work on that. Okay, so in the exam, you will be given a question booklet with sketch paper. And you're going to put your answer on some separate answer booklet. There will also be some sketch paper included as well, so you don't need to bring your own. Okay, you'll be given just one, but we'll get extra ones. You know, in the exam center, you definitely can ask for more if you need it. Okay, just a little bit easier for you to work on. All right, to start with, no calculator. So make sure you understand the basic. No calculator. And understand the basic one. For example, what is 2 to the power 10? I'm pretty sure you know, right? Okay, things like that. Okay, and then there will be very limited to none multiple choice questions. Mostly will be something you got to write on a paper. Okay, so little to none multiple choice question. Okay, and then what about the types of question? There could be some definitions. And there could be some short answer, which could be maybe asking for some explanation, and also maybe some justification. There might be some coding, but not to the extent like a programming test. I might give you some, maybe some method, for example, maybe some operation about tree for you to implement, some simple one, right? All right, so there could be some coding and also there could be some tracing. So the best way to really get prepared is maybe go over the example code that we released to you guys. You can take a look and play with them. And also there could be proofs as well. And for example, it could be something to do with the asymptotic upper bound. Upper bounds. Or it could be just to derive the upper bound, right? And to count the number of primitive operations. And, or maybe to prove the properties about tree, like what we did for proper binary tree, right? Something like that. And there might be some question from Jeff, also maybe from Sunila, from other instructor, or maybe from me. But I'll make sure any question coming from them, I'll make sure you can do them. Otherwise, I wouldn't include them in our version of the exam. So you don't need to go over the material from other section. You don't have to. Okay, you only have to focus on the material for section X and Z. Okay, so you should really study, well, basically everything. Yeah, so you're going to study the slides for sure and iPad notes. I would say start with these two. The way I normally generate question is I'll try to go over everything I have already told you guys, in the lecture, and also in the notes. I'll generate question from there. Just pay attention to what we cover, right, in the class. And also you may want to pay attention to some example code that we made available on the lecture site. And for example, the BEST node. That's just one example, right, about binary search tree. And for the assignments, I would suggest maybe you can review the solution again, but we're not going to give you that big problem to really reprogram. We might ask you some conceptual question about it. We might. Okay. So reviewing the assignment might be useful as well. You may not be asked to reprogram the whole problem for the assignments, but maybe part of it, we might ask you a question about it. Okay, that's about what I want to say for now. Guys, any question about the exam? Feel free. Go ahead.
So for open-ended questions, if we are worth multiple marks, can we assume that we are expected to provide like the same amount of concepts? So for example, if you're looking for an explanation and say it's worth 5 marks, does that mean that perhaps we should try to think of like 5 programming concepts that we should use?
Yeah, I see what you mean. If that's really open-ended, right, it's a way for us to see like how much you have understood. You definitely want to cover just enough details to convince us you actually understand what the answers are involved, right? Mm-hmm. You don't give us an essay for every question. You don't need to. Yeah. Mm-hmm. Yeah.
Will there be a practice one or?
Yeah, maybe not like a whole practice exam, but I'll give you guys an example question to try. But that one may be just about the format and some example, right? I think your priority should be review all the material. That'll be the best way to get prepared. Yeah, question?
For like tracing problems,
yeah.
Is our side work going to be graded, or is it just like the output?
Yeah, I think for tracing question, most likely the output. Or it could be that I want you to maybe look at the code and tell me which line may have gone wrong, something like that. Yeah. Mm-hmm. All right, thank you again. I'll reach out to you guys about office hour and review session. Okay, and good luck to your other exam too.